Hi, good afternoon, everybody. Welcome back for another lesson of multivariable calculus. And today we're going to be looking at section 14.8, which is known as Lagrange multipliers. Now, again, it's my firm belief that everybody in this class already knows how to do multivariable calculus with all the concepts. The only thing is that we have to then define it. We have to go through working, making sure that we can extract all of those motivating topics for us to learn. So, in the spirit of that, what I want to do is I want to list a question here. All right, and this question is going to say that we want to find the point on the line. Let's call it 3x plus 4y is equal to 5. That is closest to the origin. So this question, or this type of question, should remind you of a Calc 1 problem. All right, so this is a Calc 1 problem where we were working with optimization. So to do this sort of question in Calc 1, what we would do is we would try to find this one function that would tie in what we need. And that one function, since we're talking about closest, that one function that we would be using would be the distance formula. Oops, excuse me here. That's x sub 1 squared plus y2 minus y1 squared. There we go. We would be using this distance formula because, again, it would want to find some closest value. So in that natural sense, we would just carry out the calculations from here. We would just say, okay, well, one of the points, that's going to be the origin, so the origin is going to be 0, 0. The other point on this line, we have no idea what it's going to be, so let's call the other point on the line just x and y. And so then we would go through and we would say, okay, well, the distance formula here then would look like x2 minus x1, so that's going to be x minus 0 squared, plus y2 minus y1, which is just y minus 0 squared, just like this. And because we were working with Calc 1 type of problem, we couldn't differentiate with respect to two different variables, which meant that we have to go back and we actually have to solve one equation in terms of x. And that equation that we would then solve would be this equation right here. We would solve this equation for y, and we would say that y is negative 3/4 x plus 5/4, just like that. And what we would do with that is we would take that into our distance formula, and we would make that insertion for y. So my y value here would be negative 3/4 x plus 5/4 quantity squared. Just like that. And then what we would do is we would say, okay, well, let's take the derivative here. But in order to take this derivative, we would need a chain rule. We would probably need some sort of product rule in here somewhere, possibly. It makes things a little bit more difficult. All right, so instead of trying to find the maximum or the minimum for the distance formula, we would actually work with the square of the distance. And we want to work with the square of the distance simply because minimizing the square of the distance is the same as minimizing just the regular distance. In this new function here, we typically called some other function, let's call it g of x. All right, and what we would want to do is we would want to minimize g of x. In other words, we want to take the derivative. So taking the derivative here, we would then take that derivative, that would just be 2x, and then we would take this derivative in here. All right, so taking that derivative, we drop the exponent forward, keep the inside the same. There we are. subtract the exponent by 1, and then multiply by the derivative of the inside. The derivative of the inside is negative 3/4. So there we are. Then what we would do is we would say, okay, well, now we could go ahead and we could set this equal to 0. That way we can find some critical points. Finding these critical points would then help us find what are these values that we're looking for. So let's go through and let's set this equal to 0 to find these critical points. All right. So here I'm going to have 2x, let's say plus, and in here I have 2 multiplied by negative 3/4. So 2 multiplied by negative 3/4 is going to get us negative 3/2. And we're going to multiply negative 3/2 into this equation. So negative 3/2 times negative 3/4, that's going to get us positive 9/8. All right, good so far. Then negative times a positive, that's going to get us a negative. Oops, my apologies, I forgot the x. So negative 3/2 times 5/4, it's going to be negative 15/8. Perfect. And all we need to do from here is just solve this equation. So what I want to do is multiply both sides by 8, just so I can clear some fractions, make it a little bit easier. So it's going to be 16x plus 9x minus 15 is equal to 0. Which then gets me 9 plus 16, that should be 25x is equal to 15, which means x is 15 divided by 25, and 15 divided by 25 should get us 3/5. Nice. So as we then start looking through this, we can then see, hey, my x value here is 3/5, but the question originally was to find the point on the line, which means we need to find some y value. So finding the y value, all we're going to do is make our substitution like such, and then we go through and solve. All right, this is going to be that's going to be negative 9 divided by 20 plus 5/4. And then we just go through the calculator. Negative 9 divided by 20 plus 5 divided by 4 should get us somewhere along 4/5. Yep. So the point closest to the origin that is on the line is 3/5, 4/5. Now, why is it that I wanted to bring this into question then? Right? If it's a Calc 1 problem, well, that's back in Calc 1. But the interesting part about this is that back in Calc 1, you were actually working with Lagrange multipliers. This here is the method of Lagrange multipliers. We just need to define it a little bit more, and we need to iron out some of the details that were taking place here. So for that, I want to go to my old friend GeoGebra, and I want to view this problem on GeoGebra to see if we can make those connections. All right, so follow me along. All right, so thanks for joining me on GeoGebra. So here we are, GeoGebra. Now what I did is I put this line on here, and this line was at 3x plus 4y is equal to 5. And the question was, what point on this line gets us closest to the origin? Well, the origin has equation 0, 0. Now this point, point B, I put exactly on that point of 3/5, 4/5. And because I did that, I'm then going to be able to look at the distance between this and the origin. Now, let's say that I was looking at that distance here. Would you agree then that the smallest distance would be that point? Okay, good. So looking at that line segment, we agree that, I'm hoping that we agree, that the point closest to it is on 3/5, 4/5. Now, here's the interesting part about this. We don't really need the distance formula here. Instead, could I just consider this vector? Now, what I want to do here is I want you guys, if we were in class, I would want you guys to then describe this vector to me. What type of properties does this vector have? The one main aspect about this vector is that it goes through the answer, right? It's at this point, it goes through the origin, and it's kind of giving us that direction. And the fact about this vector is that it is orthogonal to the line. In other words, it is normal to this line. Now, I want you to think back into chapter 16, chapter 14.6, when we were looking at directional derivatives. Looking at directional derivatives, we were able to pull off one aspect of this, and that was gradients. We automatically know that gradients are automatically orthogonal to the surface that we're observing. So, let me ask you this then. Instead of looking at this line in R space 2, what happens if we look at it in R space 3? And that's here. The line is no longer a line, the line is now a plane. Well, if we have the plane, can we extract the gradient for this function? Yes, and this is the gradient. Now, the gradient, again, we're able to move that gradient, but the nice part about this is that the gradient will always be orthogonal, which means all we really need to do is figure out one question, which is, when does that orthogonal vector go through the origin, and we're done. That is the method of Lagrange multipliers. The method of Lagrange multipliers says that given any surface or any function, what you can do is you can take the orthogonal vector for that surface and just consider any scale of this amount. That being said, we now can start extracting gradients, and we can start calling them Lagrange multipliers if we know that they are just going to be, these vectors, these orthogonal vectors are just going to be scalar multiples of one another. All right, so thank you for joining me on GeoGebra, but let's now go back and let's verbally go ahead and analyze these functions with the definition of a Lagrange multiplier. All right, so welcome back to the class here. Now, here we have the definition for the Lagrange multiplier. We're going to say that assume that these two functions, f of xy and g of xy, are differentiable functions. And the function f of xy has a local minimum or local maximum on the constraint curve. We're going to say that the constraint curve is g of xy is equal to 0. And we're going to say that it has a local max or local min at some point, call it P, that has coordinates A, B. If the gradient of G, so the gradient of this constraint function, evaluated at P is not equal to 0, then there is a scalar multiple lambda, that Lagrange multiplier, such that the gradient of our function evaluated at the point P must be equal to lambda times the gradient of gradient of G evaluated at P. This is the main aspect that we work with Lagrange multipliers right here. This is what we want at all times. If we can get the two vectors to be parallel, then we would have found where that minimum or maximum is. And we're going to take a look at that with an example. So let's go ahead and let's look at this example here. This example is going to say that we want to find the extreme values of f of xy, which is 2x plus 5y, on the ellipse x squared over 16 plus y squared over 9, which is equal to 1. All right. So here's the question. So find the extreme values. Now again, back from the other class, anytime that we have this verbiage here that we want to find these extreme values, then what we have to look for is to find all maximum or minimum, whether they be absolutes or local. So that question there just says, hey, find all of this. All right, so we have some function f, and what we're going to do is we're going to create some function g of x. All right, so f of x we know, f of xy we know to be 2x plus 5y. Now g of xy, I'm going to consider that to be this function. This is going to be the constraint that we are applying to this function f. So the constraint that we're applying here, this is going to be g of xy, which is x squared over 16 plus y squared over 9. When it's equal to 1, that just becomes a level surface. Giving us a level surface, well, we know how to work with that level surface. We know how to graph it. All right, so what we need now are gradients. So let's go through and let's pull off. We need the gradient of my function f. So the gradient of the function f, remember that's the derivative with respect to x, which is 2, derivative with respect to y, which is 5. I need the derivatives, or the gradients for g. The gradient here would be x over 8. The gradient here would be 2y over 9. There we are. The method of Lagrange multipliers then says that if your function f is going to have some max or min on this constraint, then that means that their gradients must be parallel to one another. That means the vectors, these gradient vectors, are going to be off by some scalar. We got to find that scalar. If we can find that scalar, so if we can solve for that lambda, then that means we're going to go back and we're going to be able to find what is x and what is y, meaning we're going to be able to find the maximums and minimums. So that's our job. Our job here is then to use this interpretation so that we can solve what is that lambda, what is that Lagrange multiplier. So in here, properties of vectors, this is multiplying by a scalar, and it's equal to this vector, which means 2 must be equal to lambda x divided by 8, and, or we could say or, 5 is equal to lambda 2y divided by 9. Nice. So again, we want to solve for lambda, so we need to try to find what lambda is. And we're going to be able to use anything that we have given to us to aid with that process. So what I'm going to do here, instead of solving for lambda initially, what I'm going to do is I'm going to solve for x first. So multiply by 8, that's going to be 16, and then I'm going to divide by lambda. So that means that x is 16 over lambda. I'm going to do the same thing over here. Multiply, that's 45. So 45 divided by 2 lambda is going to be that y value. And the reason I did this is because now I want to use my constraint curve. So use a constraint curve. So when we use this constraint curve, we're then going to say, okay, well, my x value, the x value now is 16 over lambda. All right, that was that 16 over lambda squared divided by 16 plus the y value in my constraint curve, that y squared, now becomes 45 over 2 lambda squared. All that divided by 9 must be equal to 1. Now, given all of this, we can now go ahead and solve for lambda. All right, so that's not too bad. It gets us a pretty good value. So let's go through and let's actually solve this for lambda. All right, this is going to be 16 squared All right, so I'm going to have this 16 squared divided by lambda squared times 16, plus I have 45 squared here, and that's going to be 4. 4 times 9, that's going to get us 36, so that's going to be 36 lambda squared is all equal to 1. All right, looking pretty good so far. All right, let's see what else we could do. Try to make this a little bit easier. Here I'm going to cancel out one of the 16s. So I canceled out the 16 here, so I get 16 over lambda squared plus, see if I can simplify anything here. So 45 divided by 36, that simplifies down to 5/4. All right, so here I have 5/4. Oops, excuse me, I do not have 5/4. My apologies, that's 45 squared. So 45 squared divided by 36, there we go. That's 225 divided by 4, but then I have a lambda squared here. There we are. Now I'm going to multiply both sides by the LCD. Multiplying both sides by the LCD, that means I'm going to take 16 and multiply it by 4. That's going to get me 64. So this is 64. This is going to be plus, I multiplied by the LCD, which just gets me 225, is equal to, and this is going to be 4 lambda squared, because that was the LCD. All right, pretty good so far. So all we're going to do is add 225 plus 64. So that's going to get us 289 divided by 4 is equal to lambda squared. So 289 divided by 4, and what we're going to do is we're going to take the square root of that, that way we can solve for lambda. So let's go ahead and take the square root of that, and it should be 17 divided by 2. So we get lambda to be plus or minus 17 divided by 2. Now please be careful. Since you took the square root, you need to account for both positive and negative versions of the lambda. All right. Now, what does that mean for us? What that means is that because lambda gives us two values, we're going to have to consider both. So here it goes. When lambda equals 17 over 2, what is x? Well, x was 16 over lambda, which means this is 16 over 17 halves. Nice. Which means this is really 32 over 17. Okay, what is y? Well, y was at 45 over 2 lambda, which means this is 45 divided by 2 times lambda, and lambda we're assuming to be 17 halves, which means that y is 45 over 17. There we are. Nice. All right, the next one, lambda is negative 17 over 2. Again, we're considering both outcomes. That's going to tell me that x is the same process, but just negative. Negative 32 over 17. And then y is negative 45 over 17. All right, perfect. So we found these extreme values now. So what I'm going to say at this point in time, f of xy has a local maximum of 17 at, and I'm going to say that's going to be at the point 32. Give me 1 second, I'll be right back. My apologies, my dog had to go use the restroom, so I'm back now. Yay. All right, so a maximum value of 17, and that's when x is 32 over 17 and 45 over 17. And a local min of negative 17 at negative 32 over 17 and 45, negative 45 over 17. There we are. Now, how did I get these values of a 17? I heard somebody say, right? How did I get 17 and negative 17? Well, the way that we get 17 and negative 17 is if we were to go through and if we were to insert these values into my function f of xy. Now remember, f of xy, this was 2x plus 5y. So if I make my insertion here, which was 32 over 17 and 45 over 17 into this function, then I would get just 17. All right, and that's where I got these two values at. So what I want to do really quickly is I want to take you to GeoGebra, and I want you to see this example on GeoGebra. All right, so follow me there, and we'll see you guys in a bit. All right, so here's my old friend GeoGebra. Now, what I'm going to do here is I'm going to show you this equation of the surface. This equation of the surface is that equation that we're working with, that 2x plus 5y. All right, so here's that 2x plus 5y that we work with. Now, I'm putting a constraint on this. The constraint is a level surface. However, that level surface in R space 3 is really just this surface. Sorry, that level curve is really just a surface. Excuse me, in R space 3. And we see it here. All right. Now, I'm going to zoom out just a little bit more, just because I want to see some intersections here. All right. And I'll do that in just a bit. What I also went to do, I also went and I parameterized the intersection of these two surfaces. So notice this. That intersection has more of an elliptical shape. There it is. So when does this surface, when does this plane have a maximum or a minimum that exists on this surface as well? This surface is that equation of x squared divided by 16 plus y squared divided by 9. So, when does that happen? Well, that happens right here. That's when z is equal to 17 right up here, and that's when z is equal to negative 17 down here. That's what this looks like. This is what Lagrange multipliers are doing, is it takes this surface and it finds a maximum and minimum given some constraint values. All right, so now that we have this visual, let's go through and let's see if we can perform different types of problems. All right, so we're going to go back and we're going to see if we can work with a different type of example. All right, here we are. So here goes a question. We want to find the points on the sphere x squared plus y squared plus z squared is equal to 36 that are closest to and farthest from the point 1, 2, 2. All right, so again, we want to figure this out, and what we're going to do is we're going to use Lagrange multipliers to help with this process. So let's see if we can start using these Lagrange multipliers. All right, so I see that we do have a function here. All right, we're given this function here, and I want them to be closest to and farthest from. So because they're giving me that I have this closest and farthest, that kind of means that I'm working with some sort of distance. So what I'm going to do is I'm going to extract the distance formula in R space 3, which was x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. There we are. Now, using this, what I want to do now is I want to go ahead and I want to make my substitutions for my points. All right, one of the points that I'm using is going to be 1, 2, 2. The other point that I'm going to be using is just going to be the point that's going to be on the sphere. We don't know what that point is, so we're just going to label it generically XYZ. Which means my distance here is then going to be x minus 1 squared plus y minus 2 squared plus z minus 2 squared. And this is all the square root. Now, very similar to what we had earlier, if I'm trying to find the distance, the smallest distance, what I can do is I can use the square of that distance as my formula. Which means this is going to be my function that I'm looking to maximize or minimize. Alright, so I want to maximize or minimize this function here. So this is what we want to pay attention to. Now I need a gradient. So let's go through and let's find a gradient here. So here's the gradient. Taking the gradient, partial derivative with respect to x, that's going to be only this guy here. So that's going to be what? 2 times x minus 1. Do the same thing for y's. That's going to be 2 times y minus 2. Same thing for z's. That's 2 times z minus 2. There we are. That's a gradient. Now I also need a constraint function. What is a constraint function? Well, the constraint function that we're going to be working with, I'm going to highlight that in green. This is going to be my constraint function. And this is going to be my g of xy. Oops, excuse me. G of xyz. Now, when g of xyz is equal to 36, then that means it's a level surface. All right? So let's work with this gradient here. I'm going to grab this gradient. Gradient of g is going to be 2x, 2y, and 2z. Method of Lagrange multipliers then says that we need to consider finding when these two vectors are parallel to one another. All right, what scalar does that work for? So let's go ahead and let's work that out. All right, that's going to be when this value, when 2 times x minus 1 is equal to lambda times 2x, or 2 times y minus 2, that's this one, is equal to the lambda here, and that's lambda 2y, or the third one, 2 times z minus 2, is equal to, yep, lambda times 2z. Now the fact that we can divide by 2's makes it way easier here. So here's going to give me x minus 1 is equal to lambda x in here and here. There we are. Perfect. Now again, I don't want to try to solve for lambda automatically. I want to use one of my constraints in order for me to be able to generate what is lambda. So in that process, or in that sense, I have to go through and I have to find what is x, what is y, and what is z. So let's find x, y, and z in terms of lambda. So in here, for the first equation, I want to solve for I want to solve for x. So I'm just going to write on here as a quick note, I want to solve for x, y, and z. Alright, so let's see, let's bring lambda over here. So that's going to be x minus lambda x is equal to 1. There we are. Move that over, add that over, perfect. Factor out the x and divide by whatever's left over. So this is going to be 1 minus lambda. There we are. Do the same thing here. Alright, let's do negative 2. Let's move this y over, so it's going to be lambda y minus y. Factor out the y, and then divide by whatever's left over. So that's going to be negative 2 divided by lambda minus 1. There we are. Perfect. Do the same thing over here, but over here it's the same process, which means that z is going to be negative 2 divided by lambda minus 1, same as the y values. Awesome. So now that we have this, let's go through and let's use our constraint. So I'm right here, use a constraint function g of x, y, z. All right, when it's equal to 36. So when this constraint function is equal to 36, we had x squared. Now that's going to be 1 minus lambda squared plus y squared. That's now going to be negative 2 divided by lambda minus 1 squared plus, same thing, negative 2 over lambda minus 1 quantity squared is equal to 36. Alright, so looks like a lot of work, but it's not too bad. We're actually in a really good place here. So let's see if we can work through some of these out. Alright, so here's going to be that 1 divided by 1 minus lambda squared plus, let's see, I have 1 minus lambda. I'm going to do 1 minus lambda down here. So I'm going to move this negative right here down here. And you're going to see why in a little bit. That's 4 divided by 1 minus lambda squared. Nice. Plus, same thing here, is equal to 36. There we are. Now what I can do is I can multiply by the denominator, all right, everywhere. So that's now going to be 1 plus 4 is equal to 36 times 1 minus lambda squared, which means this over here is going to be 8, 9, so it's going to be 9 divided by 36. 9 divided by 36 is 1/4, and that's going to be equal to 1 minus lambda squared. Yeah, not looking too bad. Alright. Perfect. Looking pretty good so far. Alright, I'm going to take a square root. So taking a square root gives me that plus or minus 1/2 is equal to 1 minus lambda, which means lambda here, let's see if I can get this out. So lambda is going to be 1 plus or minus 1/2. Alright, not bad so far. So let's go through and let's find these lambdas. What are these lambda values? Alright, so lambda is going to be, let's say 3/2, or lambda is going to be 1/2. Nice. So those are the two lambda values that we get. Now that we get those lambda values, we then have to use these to find x, y, and z. So find x, y, and z. And naturally we should get two values because we're dealing with a sphere. When we're dealing with a sphere, we want these values to be close, or we want these points on the sphere to be close to this point. So naturally we should get 2 points. Alright, here we go. Let's solve them. X. Alright, actually, give me one quick second. I'm going to use one of my first lambdas. I'm going to say lambda is equal to 3/2. When lambda is equal to 3/2, I'm going to say x is 1 divided by 1 minus 3/2. Y is negative 2 divided by 3/2 minus 1. And z is the same thing. There we are. Alright. So on here, let's see, multiply everything by 2. So that's going to be 2 divided by 2 minus 1, or 2 minus 3. So that's going to be negative 1. So it's going to be negative 2. Same thing here, multiply everything by 2. That's going to be 4. So it's going to be 4 divided by 3 minus 2. So 4 divided by 3 minus 2. That's going to be just 4. Alright, not too bad. And I do believe that's negative, so it's going to be negative 4. And so that means z should be negative 4 as well. Nice. So we have one order triplet. This one order triplet that we just found is -2, -4, -4. So that's one of our answers. Let's see if we can find the other one. The other one when we use lambda is equal to 1/2. So now use lambda is equal to 1/2. So you give it a shot. Give this a shot and see if you can get the lambda values using the same x, y, and z equations that we had right up here at the top of your screen. So go ahead, put pause on the video. I'm going to put pause on the video, I'm going to work it out, and then I'm going to come back and give you the answer. So I put pause in, take some time and do it. Here's your answer. I hope you put pause because that was quick. Alright, so your answer should be 2, 4, and 4. Awesome. So, to fully answer the question, which one of these values is closest? Which one is furthest? So again, we have two values. In order to determine that, we then have to go through and use our distance formula. One of them is going to get me 2, 4, 4. The other one's going to get me -2, -4, -4. Notice the one that has -2, -4, -4 is going to get me larger values here because -4 minus 2 gets me -6, so that's going to be 36 here, 36, and then over here is going to be 9. So 36 plus 36 plus 9 gets me a really large number versus 2, 4, 4. This is 4 minus 2, that's just going to be 4. Same thing here, and then here is just going to be 1. So 4, 4, and 1, yeah, not as big as 36, 36, and 9. Which means the negative values are the ones that are furthest away. So let's summarize this. The point -2, -4, -4 is furthest, and the point 2, 4, 4 is closest to the point. And what was that point that we were given? I completely forgot throughout all of this. That's 1, 2, 2. There we go. To the point 1, 2, 2. Oops, there we go, 1, 2, 2. And again, these 2 points, they are on the sphere. So these 2 points that we found, that -2, -4, -4, and 2, 4, 4, both of these lie on the sphere. So the points on the sphere that are furthest and closest to the point 1, 2, 2 are the ones that we were given here. Awesome. So there you have it. Now, you might be asking also, well, what happens if we have more than one constraint? All right. So find the maximum and minimum of this function f of x, y, z, which is given by 4y minus 2z, subject to the constraint to x minus y minus z is equal to 2, and x squared plus y squared is equal to 1. So there we are. We have two different constraints, and could we still find this? That's going to be our overall goal. So let's go ahead and let's give this a shot. Alright, so how would we work with something like this if we have two different constraints? Well, the theory behind this goes back into what it means to be this Lagrange multiplier, right? Having this Lagrange multiplier means that we have a surface that's going to be orthogonal, or this vector that's going to be orthogonal to this surface. And at every step in time, you're looking for another surface or another vector that's orthogonal to the surface. So in other words, you're creating these two orthogonal vectors. Now, what does that then mean? When we have one orthogonal vector and then we find another orthogonal vector, like such. Well, that's going to mean that in order for us to be able to find the minimum distance here, all right, and let me actually show this slightly different. Let me make one of them larger. There we go. And that's a 90-degree angle because they will be orthogonal. Now, the shortest distance, what is that shortest distance? Well, that shortest distance is then here, given by the addition of the two vectors. So if we had initially gone by and said this is vector u and this is vector v, then what is this new vector that is the minimum distance from vector u to vector end of vector v? Well, that's going to be u plus v. And that's where the theory comes into play, that we now have to find this new vector subject to these two new constraints, because that's going to be the vector that's going to minimize this given function for the values that we're looking for. All right, not too bad. So let's go through and let's start setting this up. All right, I have my function f, so I'm going to construct my function g. So I'm going to say my function g here, which is going to be g of xy. G of xy, and you know what? I'm having second thoughts about this. I'm going to make g of xy in green. So g of xyz. G of xyz, that is 2x minus y minus z. Alright, I'm going to choose a different color for the new one. That's going to be h of xyz. So h of xyz, that's going to be my function, that's x squared plus y squared. There we go. So now I need some gradients here. Alright, so my gradient of my function f, that's going to be 0, 4, negative 2. I'm going to need the gradient for my function g, which is going to be 2, negative 1, negative 1. And I'm going to need the gradient for my function h, which will be 2x, 2y, and 0. There we are. So now let's use a method of Lagrange multipliers along with this little diagram that we have over here to see if we can find that specific minimum or maximum value subject to these constraints. So that's then going to tell me that delta f is going to be equal to lambda times the first vector, again some scalar multiple of this initial vector, plus some other scalar. We don't know what the next scalar is going to be. It might be lambda, it might not. We're going to call this mu. So this other scalar multiplied by the other function, which is going to be, or the other vector, which is going to be gradient of h. And this is what we need here. This is the equation that we need to solve in order for us to be able to find the maximum and minimum of the initial function f. And again, this is all based off of these vectors that we were initially working with. So let's go through and let's solve, or let's set up some of these equations. All right, lambda f, or sorry, del f for the x values is 0, so that 0 is going to be equal to 2 lambda plus mu times 2x, or 4 is equal to, that's going to be negative lambda, because that's going to be negative 1 times lambda, so that's just lambda, plus 2y multiplied by mu, so that's mu times 2y, and then the last one, we get negative 2 is equal to, once again, negative lambda plus 0 mu, or mu times 0. There we are. All right. So from here we can just solve one of them because for this very last equation we actually get that lambda is equal to 2. Now that's really awesome. Since lambda is equal to 2, well, we found one of them. That's great. Awesome. Check. Got it. So using this lambda is equal to 2, I'm now going to go through and I'm going to find the rest. So for the first equation here, I get 4 plus 2 mu times x, or I get, that's going to be negative 2 because I inserted in, so it's going to be 6 is equal to 2 mu y. All right, that was this equation. Perfect. So let me solve for x here. All right, so I'm going to solve for x. So solving for x, I'm going to subtract 4, and then I'm going to divide by 2 mu. Oops, excuse me. So x is going to be negative 2 divided by mu. This one here, second equation, for y, I'm going to divide by 2 mu, so that's going to give me 3 divided by mu. Now, once I have this, I'm then going to be allowed to use one of my constraint functions. So I'm going to say here, use a constraint function for x squared plus y squared is equal to 1. Now, when we use this constraint function, we're now going to be able to get negative 2 divided by mu squared plus, plus 3 divided by mu squared is equal to 1. Multiply both sides by mu squared, and we're left with 4 plus 9 is equal to mu squared, which means this is going to be that mu is equal to positive or negative square root of 13. All right, pretty good. So now that we have this scalar solved for, we actually have these two scalars solved for. We have lambda and we have mu. That means now we can go through and we can find the x, y, and z coordinates. All right, so let's go through and let's find the x, y, and z coordinates. All right, I'm going to go back down here. There we are. And I'm going to be using now that mu is equal to root 13. If mu is equal to root 13, let's find out what x is. Well, x was, according to what we had right up here, negative 2 over mu, which means x is negative 2 over root 13. Nice. What's y? Well, let's find what y is. Y was 3 over mu, which means y is 3 over root 13. There we are. Excuse me, I gotta let my dog out. All right, I'm back now. All right, so now that we got those x and y coordinates, awesome. Now, I also need to figure out one more set of coordinates, and that last set of coordinates is going to be when mu is equal to negative root 13. So when mu is equal to negative root 13, we get the same x and y, except they're just going to alternate signs, which means that x is going to be 2 over root 13, and y is going to be negative 3 over root 13. Now, yes, there is an issue here, the issue being that we don't have a z value yet. Since we're looking for the maximum and minimum, we need to find those exact values. So, which one of these constraint equations would then give us a z value? Yeah, this guy right here, the one in green. So we're going to go through and we're going to figure that out. So that's going to be 2x minus y minus z is equal to 2. So use this equation. Yep, 2x minus y minus z is equal to 2 to solve for z. All right. Now, the way we're going to do that is we're going to work with the x and the y values. We're going to work with x is negative 2 over root 13, and we're also going to work with y is equal to 3 over root 13. All right, using these values, we're going to sub them into this equation. Just like this. All right. Once we're able to insert this in, then we should be able to get that z is going to be equal to negative 2 minus 7 over root 13. Doing the same thing over here, when we have x is equal to 2 divided by root 13, and when we have y is equal to negative 3 over root 13. Again, subbing them into the equation, we should be able to extract that z is equal to negative 2 plus 7 over root 13. Nice. So, when we want to look at the maximum and the minimum values, we still got to answer that question, because at this point in time, we haven't answered that question just yet. I know. It's been a very long process. And here we go. Let's go ahead and let's solve this. All right. So lastly, all we need to do is find what is the output when we're evaluating our function f at that given or at those given points. So let's work with that. So here we go. Oh, go away. There we go. All right. So we want to evaluate the function when x is negative 2 over root 13, y is root 13, and z was this value of negative 2 minus 7 over root 13. All right. Well, your function was 4 times y minus 2 times z, just like this. Perfect. So that's what, 12 over root 13. And this is going to be plus 4 minus, or sorry, plus 14 right here. 7 times 2, 14 over root 13. There we are. Which then makes this 14 and 12. That's now going to be 26 over root 13 plus 4. That should give us some sort of maximum. Minimum now. Or we'll see if that's a minimum. The x value is at 2 over root 13. The y value is at negative 3 over root 13, and that z value is at negative 2 plus 7 over root 13. All right, making our substitutions, that's 4 times the y value, so that was negative 3 over root 13 minus 2 times the z value, it's negative 2 plus 7 over root 13. This is negative 12. Root 13, this is plus 4, and this is minus 14 over root 13, which means this is 4 minus, same thing, but it's negative, 26 over root 13. There we are. So, f has a local max of 26 root 13 plus 4 at the point negative 2 root 13, 3 root 13, negative 2 minus 7 root 13, and a local minimum of 4 minus 26 over root 13 at the point, and we get something very similar there, which is 2 root 13, negative 3 over root 13, and then negative 2 plus 7 over root 13. There we are. That's all there is. This is the method of Lagrange multipliers. All right, so again, you're going to have homework on this, which is going to be great. And later on, I'll announce on Canvas when we're going to have our next exam. All right, so that's going to be it for chapter 14. We are now done with chapter 14, and what comes next is chapter 15. So stay tuned for that, and I'll see you all soon.